Alright, this is the second video, and let's take a look at problem number 2. But before we begin, Ms. Schaefer is here with me and observing me record this video, and she pointed out that on problem number 1 in part B, 1B, that I said that the velocity at 2 seconds was 64, when in reality it's 30, or the position was 64, when in reality it was 36. That was just my mistake recording the wrong number, but the process is still the same. So if that confuses you or you have any questions, come and see me at lunch in room 312. God, help me. All right, number 2. Miss Schaefer's laughing at me. Our class takes a field trip on the calculus bus. We're flying at an altitude of 7,000 feet. Our mission is to share our calculus knowledge with the needy math students throughout the United States. Suddenly, we spot a group of children who know nothing of calculus, so we throw a set of our spiral-bound note cards along with a one-way ticket towards them at a velocity of negative 150 feet per second. Question A, Algebra 2 question. What's the position function that represents the path of the note cards? So if you look back at your notes, you know that the position would be s of t is equal to negative 16t squared. We have an initial velocity of negative 150 feet per second, so there's my t, and we are flying at an altitude of 7,000 feet when this occurs. Determine the function that represents the velocity of the note cards. And since it says the velocity, that's indicating that we're looking for the instant velocity, which is the first derivative of position. So we're going to use the power rule and get negative 32t minus 150, and that is a formula that I can use to find the instant velocity at any time of the note cards. Part C. What is the, again, acceleration of the note cards as they fall towards the needy children? So we know that acceleration is the first derivative of velocity, which is the second derivative of position. So when I take the derivative using the power rule, I get negative 32, and the units would be feet per second squared. I did not write the units back here, but for velocity, it's feet per second. And so now it just becomes simply plugging numbers in, which is simple algebra 1. D, how far from the Earth, so if we're asking how far, that's a position, are the cards at 5 seconds? So we're going to use a calculator, and we're going to calculate S of 5. And S of 5 turns out to be, if I did not make an error, 5,850 feet. But you need to confirm that to see if it's correct. Letter E, determine the velocity after 10 seconds. Well, the fact that they only give you one value of time should tell you instant velocity. So the instant velocity at 10 seconds would be v of 10, which turns out to be negative 470 feet per second. Yes, I'm just making sure I'm copying the right number. And the fact that the velocity is negative tells me that the cards are falling. And then letter F sends me back to algebra 1. See, look, average begins with the letter A, and so does algebra 1. Average velocity means change in position over change in time. So I'm going to substitute. Oh, by the way, remember average velocity. Be very careful. It's change in position over change in time. So I do not plug the 5 into the velocity function. I plug the 5 into the position function. And when I do, I will get a position of 5,800, didn't I do this somewhere? Yeah, 850 feet, which we already did in part D. And then the position at 10 seconds is, let's pause the thing. Okay, so at 10 seconds, the particle is at 30, oh, come on. I hate these boards. Oh, don't tell anybody that. 3,900 feet. So if I want the average velocity, again, remember it's change in position over change in time, so that'll be 3,900 minus 58 150 over 10 minus 5, which will give me negative 390 feet per second. Okay, hopefully I didn't make any mistakes. Letter G. G, this is almost over. At what time do the note cards hit the ground? Again, that's position. So I'm really wanting to know when is S of t equal to 0. And you can use your calculator to do that. You could do it graphically. You could do it algebraically. And then once you find that value, which I don't actually think that I did, but that's okay. Once you find that value of time, again, graph it or solve it algebraically. I would suggest graphing it. You're going to take that value of time, and it says at what velocity. So you're going to find v of that particular time, and then at what acceleration you're going to find a of that particular time that you found. Now my guess is that you're going, well, not my guess, you're also going to get a negative value of time, which doesn't make sense. So you're going to grab a hold of the positive value of time, and again, using your calculator, whoops, you're going to want this guy over here. However, you're going to do it with your calculator. Okay? And then letter H, at what time is the velocity negative 470? So it tells me exactly what to do. I want to know time, and it says velocity, instant velocity, is negative 470. So all I'm going to do here is to take my velocity function, which is negative 32t plus, minus, oh crap, t minus 150, set it equal to 470, solve that equation, which I'm, thank you, Ms. Schaefer, negative 470, which I'm not going to solve for you. T turns out to be 10 seconds. Okay, now hopefully what you find from this video is that this is very easy. If you're having trouble, look at your notes, do whatever you need to do, but your assignment is in the packet, page 14, problems 2, 3, 8, 13, 21b, and 23, and the answers are in the packet. This is also on Edline, so I expect you to come in on Monday ready to rock and roll and having understood all these problems, or either come in with your questions. Have a good weekend.